in the Unit 5 exam next Thursday. So what's happening? Today, the final lesson and the lab on kinetics. You'll find most kinetics labs. You would love to see a kinetics lab on the Cambridge exam because they're actually usually pretty simple to do, the way that they test them currently. On Tuesday, you have a review day, and I will build in a full review day, so we'll be doing practice questions of everything that we've done in this unit. Where did we start this unit at? You remember? What was the beginning of Unit 5? What was the first thing we learned? Calorimetry. So going back over Q equals MC delta T, going over experimental enthalpy calculations, right? The Q over the moles, and then the theoretical enthalpy, which is delta HF, delta HC, and then bond energies, and then kinetics. We did all of that. That's all what's going to be on the test. When is your test? Thursday. So Thursday is the Unit 5 exam. Also, on that note, you should have noticed, or you may have noticed, the paper 1 quiz questions are posted as of last night. I posted them on Google Classroom. Whenever you see that post, you should know your test is coming within the next week, right? So the paper 1 quiz questions, those are due next Wednesday. Paper 1 quiz questions are due Wednesday at 11:45 p.m. That's when Quizzes closes it. Once it's closed, you can't go back in. It is a 0 if you don't start it. And get through it by then. Make sure you're not procrastinating. Some of you have gotten bit by this, where you procrastinated, you didn't start till it was due, and it closes automatically. So make sure that you are starting on your paper 1 quiz earlier. How early could you start working on it? Today, because we're done with content today, and I'm building in a review day in between. So because review is taking place in class, tutoring next Tuesday is just going to be for individual help review and like working on any outstanding homeworks or even the paper 1 questions that you have, because we'll be reviewing in class that day. So the tutoring won't be a formal test review. The tutoring will, like it was for the quarterly, it'll be just more or less homework help and anything that you specifically need assistance with, if that makes sense. Make sense? All right, so Tuesday review day, right after class, we've also got that tutoring that we always have. And then paper 1 quiz due Wednesday, Thursday Unit 5 exam. You will be receiving a paper homework today as well. Remember, I didn't give you one last class. You will be receiving paper homework today at the end of this lesson before I do the lab. All right, ready? Let's go. Happy Friday. Yeah? This class moves like that. We got to get back to organic, like ASAP. Because the next organic unit is really loud. What? Everything okay?
That's what he's been doing. That's why I want to switch seats.
Stop whatever it is you're doing. So, let's go ahead and get started. These objectives we actually did last class, but I am going to be going quickly back over them today. That's why you see them copied in. We went over the definition of activation energy. They say to define it as the minimum energy required for a collision to be effective. So in order to have an effective collision, you need enough energy. This energy is called the activation energy. Sketch and use. Sketch. What does sketch mean? Draw it yourself. Sketch and use what we call the Boltzmann distribution to explain the significance of activation energy. We'll go back over that in the beginning of today's lesson. Explain qualitatively. What does qualitatively mean? Numbers or no numbers? No numbers. Qualitative means words. Words, not numbers. Explain, in terms of the Boltzmann distribution and effective collisions, the effective temperature change on the rate of reaction. And so that is what we ended with last class, we're gonna review it again today to make sure we're good here because there's a lot of questions because I told you I took one part out of this unit and put it in unit 7. That means that there's more questions on what we have done. So a lot of questions on the test will be on these topics. And you'll see that with the practice questions that you do online for the paper 1. Homogeneous and heterogeneous catalysts. So underline these 2 words. We're going to go over it today. You'll notice it's not mentioned in the objective, but they mention it as the title. So I would say you definitely have to know the difference between a homogeneous catalyst versus a heterogeneous catalyst, which I will explain today. It means the same thing as homo and hetero usually mean. Homo meaning same, hetero meaning different. But we're going to look at what's the same and what's the difference about a homogeneous catalyst versus a heterogeneous catalyst. And so what we have to do here, this is, if you see it printed like this, it meant I was too lazy to type it all out. So I just copy pasted it from the Cambridge syllabus, but it's the same words. Explain and use what is a catalyst and what is catalysis. And it says explain that in the presence of a catalyst, a reaction has lower activation energy. So when we have a catalyst, it will lower the amount of energy needed for the reaction to take place. Explain what happens to the Boltzmann distribution as a result of this, and then construct and interpret a reaction pathway diagram in the presence and the absence of an effective catalyst of a catalyst. So, like I said, I'm going to bring a fun catalyst. I ordered it on Amazon. I'll have it to show you next class. Also, if you did elephant toothpaste, you actually did something with a fun catalyst. It makes the reaction go. If you were here for spooky science, one of the years, because we usually do it then. But we're going to go over the theory today. So here we go. We're going to want to get this done in the next 25 to 30 minutes. The lab itself is actually really quick when you do it today. You'll see it's one of the fastest labs we'll do all year. First of all, what is a catalyst? A catalyst is a substance. What do we mean by substance?
Liquid mixture or something. So anything in the molecular?
Yeah, it could be any one of the small representative units. It could be an atom, it could be a molecule, it could be a formula unit. So it could be either an element, it could be a covalent compound, or it could be an ionic compound. But the purpose of a catalyst, and this is the exact reaction I'm going to show you next class. And I believe I had us do it small scale and pre-ACE, but I'm going to try to do it a little bit more dramatic next class. Is this one. Catalysts, if you'll recall, they get written on the top of the arrow. This is something that I did bring up in the previous class. Why do we write them on the top of the reaction arrow and not with the reactants or the products? Remember? Right. Does not react itself. It basically helps the reaction to go faster. And we're going to go over exactly how it does that very shortly, but it is some kind of species or substance that helps the reaction to go faster. So if I've got hydrogen peroxide and I've got manganese dioxide, which is what I purchased, what will happen is I will speed up a reaction that's already going to take place, which is the decomposition of hydrogen peroxide into water and oxygen gas. It will give a dramatic effect if it speeds up really quickly. Hydrogen peroxide decomposes over time very slowly, but we can get it to go faster if we add a catalyst. That's the idea of the catalyst, what it does. It makes reaction go fast. So in the simplest format. And there are several different catalysts we can use. MnO2 is one of them for this reaction. Another one, the one we used for elephant toothpaste, was Ki, another example of a catalyst that's used. If you study biology, you'll know that enzymes are also examples of catalysts. They are proteins that help a reaction go faster. Same idea. And one of the reasons that I actually taught this unit, I was debating between it, but I taught this unit before going to organic part 2, is inorganic part 2 is all about reaction. And a lot of times there's going to be a catalyst in that reaction. So it'd be important to know what a catalyst is before we go study those organic reactions. And that's why I covered this short unit before we go back to organic chemistry. All right, so what happens, going back to, just to review what we did last class. Last class, at the end of class, we talked about something called a distribution. What was a distribution again? What is the Boltzmann distribution?
It's like a bell curve?
It's a curve, but it's not a bell curve. It's a graph that tells us on one axis is the proportion of or number of
Molecule.
molecules, right? And on the other axis is the amount of
Energy.
energy of those molecules. And the way to interpret the graph, it depends on different temperatures, but one of our objectives is we actually have to sketch this graph, right? So the way to understand the graph is something like this. Not quite a bell curve. But what it describes is that in any sample you have of reactants, there are some molecules that have near zero energy, like anything that's under the curve here almost has zero energy, like very close to zero. And you have some molecules that have a lot of energy. I use the example of boiling water, and that if you were boiling water, that you would have some molecules at the bottom that were moving a lot faster than molecules that were at the top, because heat's applied to the molecules at the bottom more, right? So it's not homogeneous throughout. And so then there's also a little line here. And what represented that line? That itself is the activation energy, or what we call EA. And any molecule that's on the right side of that line would be what? Molecules that have enough energy to? Yeah. Energy to, and the wording we use for that is effectively collide. So only the molecules on the right-hand side have enough energy to effectively collide. So if you take and you look at the whole area under this curve, and you look at this section, is this all the molecules you have?
No.
It's just a small portion of them, right? So a small portion of the molecules you have in a sample have enough energy to collide. And so what we do in industrial chemistry is we alter conditions to make more molecules collide effectively. Does that make sense? Like we would change the conditions in some way. And one way we would change the conditions is by altering the temperature. And so if we increase the temperature, the amount of molecules that can effectively collide would increase or decrease. If I increase the temperature of reaction, what would happen to the molecules? We said it in the bell curve. Their energy would increase, right? So you would end up with more molecules, a greater proportion that would be able to react. And you had seen this graph last class. This was it. And so do you have to memorize the structure of this graph? The basic structure?
Yeah.
They said to sketch it, didn't they? Sketch means create it. So yeah, you have to know the basics. So that means I would memorize the basic structure of the graph, like knowing what are on the axes and knowing that there's activation energy here. Anything on the right side effectively collides. Anything on the left side does not effectively collide, right? And then you also need to know, if you increase the temperature, how does that affect the Boltzmann distribution? So at a high temperature, so T2 stands for higher temp, and T1 stands for lower temp. You need to note that at a higher temperature, more molecules effectively collide, because more molecules have an energy higher than the energy of activation needed for the reaction to occur. So you have to understand that changing the temperature changes the curve, alters the shape of the curve, and how does it it alter the shape of the curve specifically? And you do need to memorize it.
It lowers the peak.
It lowers the peak, and the peak is at a higher energy, right? So it lowers the top of the peak. It basically like flattens it out. But it lowers the peak at a higher energy, right? Lowers the peak. Peak is at a higher energy. So this means that your molecules have a higher average energy if you've increased the temperature. And that makes sense if you say it. If I increase the temperature, my molecules have a higher average energy. Does that statement make sense? If I increase the temperature, my molecules have a higher average energy. And more will have enough energy to react. Why am I being so clear about this and reteaching it? Because we have to understand what's the difference if we change the temperature versus what's the difference in adding a catalyst. Because those are the two ways we can affect the rate of the reaction. We can either alter the temperature, and that will change the curve, or we can add a catalyst, and that's going to change something else. We also know we can add the concentration. Like we can change the concentration. If we change the concentration, that just means we've added more molecules into the mix. If we add more molecules can react. So that will make a faster reaction. Let me know when we're going to move on. And am I going to put a lot of questions with the graphs on the test next week? Yes, that's why I'm saying it a second time. What I said last class, I'm teaching it again. Expect a lot of Boltzmann distribution questions. A good portion. All right, so this was a question I did not cover with you last class. I covered a similar one, but not exactly. Let's take a look at it. It says you've got this Boltzmann distribution, and they are asking you if you have a dotted curve and you have a higher temperature, what is the dotted curve compared to the original one? That's the first thing. And then they also say, what is the H, the activation energy at high temperature? So which of these would be correct? What would we be looking for to happen?
Okay, so it's not A or B. Because the peak is this.
So dotted curve has to be lower
Yeah.
and to the
Right.
right, right? So it has to be either B or C. So B states that the activation energy changes when we change the temperature. Is that true?
No.
No, the amount of energy required for the reaction to occur is still the same. So the answer must be C. So changing the temperature doesn't change the activation. Doesn't change EA. So why would they even ask us that? Because something else does change the activation energy. What changes the activation energy that was stated? Catalyst. So they're seeing if they can trap you here. That's why it's an option. So we're going to talk about catalyst now. How does a catalyst affect the activation energy? I was reviewing over the 2022 standards, and I took out one of the old objectives that they changed in 2022. For the most part, they've been revising the objectives and taking a lot of the bio standards out, like biology-related standards out of this class. They used to test enzymes in this course. They no longer test enzymes. So they really didn't test them very much, but just like to know what it was. So I used to have here, how does enzyme affect activation energy? But enzymes are actually just catalysts. So this is my terrible graphic design work. I just, it's like one of those memes where you just put a word on top of a word. Cross out activation energy without catalyst, activation energy with catalyst. So I just altered the graphic as easily as I could. And so how does a catalyst affect the activation energy? We know that a catalyst speeds up the reaction. It does this by lowering the activation energy, meaning you only need that much energy for the reaction to happen with a catalyst instead of this much energy. Does that make sense? Without a catalyst, you need from here to here. The amount of your reactants to the top of this hill. But with a catalyst, so this is with catalyst, you only need a small amount of energy for the reaction to occur. So a catalyst finds another mechanism, another way for the reaction to occur. Do you have to know exactly how it does that in this course? No. That is something held for the A-level discussion. So that's something that's discussed in the A-level is how a catalyst would lower that activation energy. We go over like the steps of how that actually happens. But here you just have to know, okay, without a catalyst, the amount of energy I need is that much. With a catalyst, the amount of energy I need is that much. So a lot less energy is needed for the reaction to occur. So adding a catalyst changes the amount of energy needed for the reaction to, right, and specifically reduces the activation energy. Doesn't change the enthalpy at all. Does the enthalpy of the reaction change as a result of adding a catalyst?
Yes.
Enthalpy is from here to here, right? This is where delta H is. Do you agree? Does a catalyst affect enthalpy?
No.
Because they try to trick you there too. They could ask that. And the answer is no. Catalyst does not affect enthalpy. It affects rate of reaction. It doesn't affect the difference between the energy of your reactants and the energy of your products. It affects your pathway. How do you get there? What type of diagram is this called, by the way? I think it was mentioned, bless you, in the here. It's called a reaction pathway diagram. We called it in the first lesson an enthalpy profile diagram, where we gave the energy of the products and we gave the energy of the reactants. When we include the activation energy, it instead is called a reaction pathway diagram. And so that just gives you your starting energy of your reactants, your activation energy, and then the energy of your products. What do they say you have to do with that? What is that word? You have to make it. Yeah, and interpret it. So should you memorize the structure of this? Yes. You should know reactants, products, and then the activation energy is always, oh, question. Is activation energy endothermic or exothermic?
Endo.
Always endo, right? EA is always positive. Never negative, because it always takes energy for a reaction to occur. It doesn't go like this, like it doesn't go whoop. It always takes energy to kickstart the reaction. So it's always positive. Yes? Okay, so then how does a catalyst affect the Boltzmann distribution? If what a catalyst does is it affects the activation energy, what does it then do? In lowering the activation energy, it doesn't change the shape of the graph like temperature does. It changes the position of the activation energy, right? So it doesn't change the shape. It moves the activation energy back. So this is with a catalyst, and this is no catalyst. So with a catalyst, you need less energy for the reaction to occur, so naturally, would more molecules have enough energy to react if given the same distribution of energy with the catalyst? That answer should be yes, right? Without a catalyst, you only have that reacts. With a catalyst, you get all this extra amount of molecules that can react. So what happens when you add a catalyst is you move the amount of energy required for the reaction to take place, you move it back on a Boltzmann distribution or to the left. So then, I know that I did 4 per slide, so this may be hard to read. I don't know if it's, I can read it, but I don't know. It may be hard to read. So the diagram shows the Boltzmann energy distribution curve for molecules of a mixture of 2 gases. For a reaction to occur, the molecules must collide together with sufficient energy. EA is the activation energy for the reaction to gases with the 2 values shown. One is for the catalyzed reaction, one is for the uncatalyzed reaction. Which pair of statements is correct? This is EA1, and this they're talking about EA1 just in case it's hard to see, and this is EA2, and this set of statements is talking about EA2. So statement A. Does EA1, is EA1 the catalyzed reaction? Yes or no?
No.
That's the one without a catalyst, right? So take out what option?
A and C.
A and C. So now we know it has to be B or D. All right. Does an uncatalyzed reaction, I think we can already figure it out. Does an uncatalyzed reaction have fewer or more effective collisions? Think about it. No catalyst. Fewer or more effective collisions?
C.
What do we say?
B.
B. And then EA2 catalyzed would be more effective collisions. The answer here is B. Are we okay with this?
Yeah.
So this is catalyst, no catalyst. Yeah, but not that. Not that. I told you it'd be. I told you it'd be quick.
Where's my phone?
All right, so let's continue.
Where's my phone?
You're gonna notice that there's a lot of these graph questions on the paper 1, by the way. I've looked through a ton of paper 1s. You can guarantee to get most likely out of that 40 questions on a paper 1, like 1 or 2 questions that have this graph or the other graph, the one with the activation energy on it. So make sure you study the graphs. All right, so let's take a look at this one. In the diagram below, they give you 2 different Boltzmann distributions, P and Q. One for high temperature, one for low temperature. And then they give you 2 lines, X and Y, one for activation energy without catalyst, one for activation energy with a catalyst. And they say which curve and which line is at the higher temperature with a catalyst present. So first, which curve is the higher temperature? Here. So we know that this is going to be either C or C. Now, which one has a catalyst present? X or Y?
X.
X. Because the activation energy was moved back. So the answer here is C. Good? So you really have to know these graphs, right? So you're not studying. By next Thursday. All right, so last thing. I had mentioned that although there's no standard that says homogeneous and heterogeneous catalyst, the title of the standard, like the whole topic, is called homogeneous and heterogeneous catalyst. So you should know the difference between the 2. And so there are 2 types of catalysts that can take place. One type is a homogeneous catalyst, and this actually means that your catalyst is in the same phase or state of matter as the reactants in the chemical reaction. So for example, if your reactants were gases, your catalyst would also be a gas. If your reactants were aqueous, your catalyst would also be aqueous. This is what we call a homogeneous catalyst. So the states match. If we we have a heterogeneous catalyst, this means that our catalyst is actually in a different state of matter than the reaction is catalyzing. We've actually already seen, I believe, an example. CO plus NO, ring a bell?
Yeah.
Makes CO2 plus N2. Anybody remember what this reaction is? Ring a bell?
Yeah, that's the catalytic converter.
Catalytic converter, right?
Yeah.
What was used as a catalyst for the catalytic converter?
Nitrogen oxide?
Nope.
Carbon monoxide?
That's a reaction.
O2.
No.
Oh.
Yeah, like a metal. It takes place on the surface of a metal in the engine. A metal such as something like a nickel or a platinum, right? What state of matter is a metal? What is the state of carbon monoxide?
Gas.
What is the state of nitrogen monoxide?
Gas.
So if the state of your catalyst is different than the state of your reactant, that means it is
Heterogeneous.
heterogeneous. So if the catalyst is a metal where the reaction is taking place on the surface of that metal, whereas the actual things that are reacting are gases, then you have a heterogeneous catalyst. That's the idea. Kind of make sense? And it says here, this is going to happen in your organic reactions coming up soon. So you're going to see tons of examples of this when we get to organic part 2. Most heterogeneous catalysts are solids that will catalyze gaseous reactants or aqueous solutions. So, is this reaction an example of one that has a homogeneous or a heterogeneous catalyst?
Heterogeneous.
Heterogeneous. Why?
Because the V2O5 is a solid and
Right.
the reactants are gases.
Yes. V2O5 is solid. And could they ask a question like this for a point?
Yes.
Whereas reactants are gases. Shouting out the different states of matter is what you have to do. And then the second question here, and I think we're almost done, right? This is the last slide?
Yes.
Explain how a catalyst increases the rate of the reaction in terms of activation energy and the distribution of molecular energies. So how does it increase the rate of the reaction? What do we got to say?
It doesn't increase.
It requires less energy for the reaction to occur. And the fancy word for that is? It lowers the,
Activation energy.
we should use the keyword. It lowers the activation energy, which if you said the energy required for a reaction to occur or certain reactions in the product, those accept it because that's literally the definition for activation energy. So if instead of saying activation, it's the same thing as effective nuclear charge. If you can explain it's because the nucleus is more positive because of the amount of protons, instead of using the word effective nuclear charge, it's the same idea, right? Or you can just say the keyword. The keyword here is activation energy. Yes? All right. So that's it for this unit. Oh my gosh. That was a fast unit, right? It just felt like it was actually 5. Believe it or not, it's just 2 of them were before the unit exam, and then 3 of them were after the unit exam where we had the lessons. So you have a test coming up. It is on Thursday. This is one of the smaller tests, just like the first test you had, so it has less content on it. That doesn't mean don't study. It actually means you need to study well, because there's less content on this. Remember that the next test, the organic one, is going to have a lot of stuff on it. So you want to try to do very well here. Unit 6 will be a long unit of study. Before we start reviewing though, what are we doing today for the second half of class? We actually have a lab today. We still have over an hour in class. And this lab will be pretty quick. So before I give you the lab and before you move to the back, let me give you the homework. I can't forget that. Don't move yet. No, I cannot.
Homework that I have to do.
Well,
I also have to teach myself.
Your own fault.
It's your
Okay,
own fault. You said it yourself.
I was ill.
You said it yourself. I still think it's cool. I just
Okay, just because my parents don't care for you doesn't mean mine don't, okay?
Let her
Yeah,
down.
believe here.
Look, look.
Don't forget to put your homework away before we get started with the lab. Put your homework away.
You can walk in. You've been really sick, huh?
There you go. There you go.
That's great.
All right. So a couple of things I need to say about the lab today, so I will need to get back your attention.
No, he's talking about.
So, first of all, the materials you'll be working with before we get started in today's lab. Let me get everybody's attention now. Just a few minutes to talk about what we're going to do, and then I'll set you off to begin for the lab. First off, we're going to be working with 2-molarity hydrochloric acid, and we're going to be working with sodium thiosulfate. What do you think the safety precautions are? Gloves and protective eyewear. Because you are working with 2-molarity HCl that is sufficient enough to cause damage. So you want to be careful. You want to be safe. Yes, Alina.
Do glasses count or just like?
That is up to you on this one. Just be careful not to spill. If you want to be extra careful, then you'll wear your goggles. So far so good? Safety, we're going to grab gloves. We're going to grab goggles before we begin. Next thing, just be careful because the glassware you're working with, you have multiple measuring cylinders. It could break really easily, so be very careful when you get to the tables. You will need to move your chairs to the back, but try not to jiggle the tables around very much as possible. There are 9 lab groups. There are 18 of you, so you're going to be working today in pairs of 2 specifically, pairs of 2. Because it is such a quick lab once you get started, you do need to turn it in today. You need to turn in the lab, you need to finish it today. I'm telling you, it's going to be quick. What you're actually going to be doing today. So you're going to be measuring the rate of a reaction, given different concentrations of thiosulfate. How are you going to know that a reaction is going to take place? You're going to have something called an insert that they're going to mention. And it's literally just a piece of paper that has the letter X drawn on it. You're going to do your chemical reaction on top of this piece of paper. What do I mean by that? You're going to place the beaker that you're doing the reaction in on top of the paper that has the X. Then what you're going to do is when you make your mixtures together, you're going to use a stopwatch to record how long it takes for the X to disappear. So you'll no longer see the X after a certain period of time. And you're going to record how long it takes for that letter to disappear on that insert. And that is going to be something to help you to determine the rate of the reaction. Then what you're going to do is you're going to change the concentration of one of your reactants. And then you're going to measure the amount of time it takes for the X to disappear when you change the concentration. And they'll tell you how to do that in here. There's a couple of things you need to know. In this reaction, you make sulfur dioxide. Sulfur dioxide is a mild irritant, is the best way I can say it. So you are provided with something called a quenching bath. Anybody ever heard of that? Okay, so a quenching bath is basically if you want to remove the sulfur dioxide from your area, when you go to throw out your reaction into the waste beaker, instead of putting it just in the waste beaker, you're going to carry your waste over here to the fume hood. And you're going to dump it in this container. This is the quenching bath I have set up for you. Once you've done that, you can close this hood. And guess what happens? It goes out into the, like it goes through the fume hood and not into the classroom. So your quenching bath is going to be in there. And when do you need to use the quenching bath? After you've done each experiment. You're going to be doing 2 experiments. You're going to change the concentration of your S2O32 minus twice. Again, these instructions with me in here. I just wanted to bring up what certain things are and where certain things are at. The final thing, they're going to ask you to make a table. I went ahead and I helped out. This is the table you should make. I have it here, so when you're ready to construct your table, for each of your experiments, you're going to need to record the volume of each of the things you're mixing together, and you're going to need to calculate, so you will need a calculator, the rate of the reaction, and it will tell you how to do this in a simple manner. And so that's the table that you need. The final thing you'll be asked to do is suggest 2 additional experiments by altering the concentrations 2 additional times, and that's what you have to figure out when you're done with your experiments. So now, I'm going to pass you the lab paper. Once I pass out the lab papers, what's the first thing you should be doing? Write your name, and after that, gloves and goggles, and then head to the back. Start reading to make sure you understand what to do, and then get started with the lab. You have the rest of class to complete the laboratory informative. Everybody needs to turn in a copy of the lab. There you go. There you go. All right, if you're moving from your seat before I pass you out the papers, if you don't have a copy of the lab paper, because you moved from your seat. Ooh. All right, so everybody should be moving and grabbing gloves and goggles. There are large and medium gloves. There are
Sophia.
Like everybody with their number, if they run out, then they may ask for it. And we're always allowed to give them. Same thing on your paper tray. You're always allowed to. Except for more time. Can't do it. You guys for more of the thing. All right, so go ahead, head to the back, start getting settled in, grab your safety attire, and we can get started. So you need gloves. Make sure you read carefully through the experiments, what you need to do. Also, you can help them with the table and pass out, you know where the rulers are at? You should pass them. Yeah.
How did you already?
They need rulers
Already?
to make the tables. Yeah. Welcome back. I think this may be your copy. I don't know if I left one at your table or not. Alrighty. That's where you're on your table. 500.
Read that right?
I did the lab earlier. I did the back note that there is no 500. You guys work so well together.
See, I have these things sometimes.
Yeah, but you have to be super good.
I'll do it.
I have 80 people and 9 tables. The guy has to match.
Wait, do we start timing like as soon as
We have the last one. Or technically at the last 40 centimeters. Oh, that's what Diane's table must have. 40?
Add the 20 and then for it here. Add the 20. Start adding the into the.
So when you add the last thing, that should be on top of this.
Remember what's
When you add the last one. This had nothing.
Yeah.
So this is the start and stop button. Start, stop, restart. So when you see 0, 0, it's going to go. You just press the button to start, and you press the same button on top. Then this button will go 50 centimeters.
I know. Start, stop.
Start, like play around with it, make sure you know how to work it. I got it right here. You definitely can't use your phone. So read what you get. If you get a timer, you get this. You must know how to use that. Yes? Well, what is the sequence? You put comfortable with time.
Oh my god. Wait. You pour it in there. Stir once and I start the timer. 5. Ready? So when you finish it, let's say slow or whatever. I just wait till it disappears.
Well, it's just water. That's water.
I don't
That's
know.
water.
No, yeah.
There are paper towels over there.
Well, we're waiting. Stir a little more. Yeah, right. What does it look like? Is it still there? Can you still see it? Wait, stop seeing it.
Oh, I figured it out.
Take a whiff.
Well, stop. So what are you going to do? If you make one sheet, he does it over there. Yes? You like that word? Punch. It's a punching bag. And then you clean it up and get your extra. Sure. Okay. So let's take a look. 0, 0, 0. So we need to make sure it's not 0, 0.
That's exactly what I was trying.
So basically, you're going to do the text mode and press this and press that button. Once you see 0, 0, 0, this button is the one you press to start. It's also the button you press. You're going to want to practice this before you get started. Exactly like you know how to do this. Because on a Cambridge exam, you can't do it. So the middle one changes your mind. My press doesn't change it to the time. Is that accurate? No, but it's saying it's called. You said it was. You want the 0, 0, 0. So you press this to start. This same button will stop. And now when I restart, hit back to 0, and you press the other side button. So start, stop. Play around with it before you actually okay? Anybody else that needs help with their stopwatch, please let me know. How do we use this? I will time it correctly.
You good? You sure? Do we do that again?
You need to do it again.
I'll have to do it out.
Start it again.
No,
Punch
it's
it.
different.
Punch it. That makes us move through, right? Punch it, and do it again. You can all mark it up and make that. You have enough for the next one. Okay.
Pour it in and then ready.
I'm assuming they're.
I don't know what you did, but I'm a little concerned. Like the reaction
my god.
But that's no reaction happening right now. Everyone else can go. Only sure once. Like tell them to stop. All right, let's take 5. Yeah. I'm a little worried about lactation drinks right now. But I don't know what y'all mix together. Like, you mix your stuff.
No, we missed
what?
it. No, we don't. This, we dumped it back in the
Okay, let me know.
This is the right one.
That's 10.
No. I mean, I'm curious.
5, 10, 20.
No? Okay. Yes, you're wrong. No, the first time I did it right. You sure? Yeah. Yeah. Sure. Yeah. You want the second experiment? No.
Yeah, that's like you
Okay, now we do the second one.
You'll need to stir it once and then you put it on the end. Right? Have you started timing? You're supposed to time it as soon as you add like the last thing, or I guess you don't have to clean it. Right? When you add the second thing. That's when the reaction starts. Stir it, it makes it happen. And David.
This goes in there. Put it in there. In there.
Yeah. Like it was there, it was clear, not that it's working the same time. Okay, start over, punch that, punching that. And then, I'll give you that.
Right now, I got stop watch. Makes sense. You're holding on to it. No, but what if it's something, right? That's not what.
Okay.
We don't know what it is.
Jenny, I think I have a task for you. I think I have something for you to do. Yes, yes, we can. They're running low on it.
So short. They're catching up. They're catching up. You're not.
If they have an unlabeled big beaker, that's a big beaker. But you technically don't need a big beaker because they have the punching button. So they
We're just going to start.
We said the wash. And you also have a waste beaker here. Okay, so I have a job for you. They are. So they're right there. So 10. Alright. It's 20.
Into the same fingers.
Here and then
Okay, don't add yes. Don't add.
finally you need the water and you stir it. Punching back is on the other side. Sophia, do you know where the punching back is? So you can do that? Yes. Just make sure you clean this with the water. This is already and then yeah. You need help. You just dry it with the paper towel so it's really dry.
Oh yeah.
Yes, I mean. What's the reaction?
Okay, 1 minute, 30 seconds.
Disney part? Did you put a little bit of water?
Yes, so that's what it's
Wait, rewatch the video.
So what I would do is almost yep, almost the whole way up. Leave it in there. If you run out, then you've got the other water there. And you can throw this out.
No, but I think my name is there. That's okay. For a while. What?
Or do we have to?
There you go. So get it to like 9 or 10.
You go where?
So what you think? Which means like the first one? The first one had a catalyst, so that concentration doesn't matter. So what you have observed exactly what you should. make the correct table, and you have to propose 2 more experiments. On the back. You're done with the experiments on the back, right? Yeah. Yes.
Oh, so we're basically doing the same thing, except we're going to less Fa5 and distilled water. That's Fa5. Okay, so according to the okay, 20 cents.
Do we well?
Versus the other one. Use the 50 cents.
And then tie it up with the other you may need a longer. You may need a longer.
Why do I? Just the 100 one.
It starts here and it turns up. Because in the reaction. Alrighty, so then I just all 7 marks before leaving and then turn it into the period 6 bin. After that, if you have time, you can work on your homework. So there's a fast lap. Okay, yeah, that's fine. What's the S minus 1. Here. You divided by S minus second. Labeled water is labeled water.
You took it seriously?
Alright, so you have to make the table correctly, then you have to answer this question, and then you have to propose 2 more experiments. They record your results in a table, and they tell you what you need to achieve. I wrote it there. No, you should read what they tell you to do and do that. Because it says, the volume of the water. Volume of liquid water, reaction time, and rate of reaction. Like whatever it says here, that's just your problem. Whatever they tell you. So it's not that you have to memorize a specific thing, it's just what they tell you. And then I would know that, you do this for both experiment 1 and experiment 2. You make a little grid.
Now, start.
What? You got 9. You got 9.
2000? Once you're done with that, you're actually gonna get a couple of minutes. Tables are done. Yes. No, don't stress. You can time. If you get the clock back, you get other people.
It's gonna take.
I support our results.
That's what I would expect, because I support the results, support it.
You not? Do you think we did wrong? Yeah. You did right. No, I was gonna say, yeah, it's too late.
Remember, for graphs and diagrams, you should use pencil on a Cambridge exam. So if you find that you need to change something, you're allowed to use pencil for graphs and diagrams on a Cambridge exam.
And we're done. Done with the experiment.
Okay, so what you will need to do is, for all of you, you're going to dump them all out in the sink, you're gonna run water. And you want to fill them slowly. The one that has nothing on it, you start lining them up there. If you want beforehand, you can take paper towels, so that when it dries, it's and so you also need to take away water off the heater to the police stuff. So you clean them all in the sink, all the heaters and tables that are done, and then put them upside down in the back table. The one that's completely empty in the back. No food for this. There were no food at the table. And the table right here, you can line everything up there in here. Oh, there's no food at the table. Yes. Okay. I'll be right there. Essay 4 first. Essay 4. And then I'm coming back to essay 5. Yes.
The other answer.
You have to come up with different amounts. Prepare a table to show 3 further experiments. You have to show your observations and distill water. And you're not allowed to distill water without vibration or less than. So the exercise here is think about the hour volume. You add it to the.
You know,
So now you can move on to whatever it tells you to change in such a way that they all have the same. Yes? If you get confused with the part where you suggest the other experiments, let me know, and I can lead you in the right direction on what you need to do.
we're doing 3 different experiments.
Yeah.
So that means for FA5, you have to choose different one.
Oh, I think you can't change them all.
Okay, so here is just further here. Yeah.
Really, Alex? Really?
Yeah.
I got it. It says right to that. I don't know if this is why I'm on that side.
Why are you only taking it in five?
Because
Update from. Nope, no update.
What was the total volume you added in
Yeah, we can do like 30, 30, 30. 30, 30.
every corner is 20 and less than 3? So every corner was changed. SA5 was 40 and 30. I mean, in 23, and water was 0 and 47. All the volumes always added to 6. And 20 of those are always the SA4. So you don't want to change SA4. Because if you change SA4, you're changing the material. It says only to change the SA5. Choose numbers for SA5 that are not 20 and that are not 40. And they all have to add up to 60. So,
That's all.
remember graphs and diagrams can be written in pencil. Yes. Can we count my real quick? Just, you should always do time and seconds.
You have turn one.
Time and seconds. Yes. 1,000 divided by 1,000. Oh. It doesn't say, right? It doesn't say you have to have. All you have to work is back. Yeah, you don't really. Check what you have here. Yeah, you did it really well.
I'm ready.
Correct. How did you come up with that?
It's rather than experiments to our day.
That we're not 20, that we're not 40. Exactly what they wanted from you.
There's another one out of this.
So you are great to start working on the homework. That was it. Because it's not there, it's like, it is typically a black box. Here. That's enough time to get started on those graphs. Make the best use of your time. Any questions here? You can change the SA5 and you can change the water. You should not be changing the SA4. Do it. You make no sense. You won't be able to. Because you're not doing the rate. Because they're telling you they're not doing the experiment.